let's just continue with our oxo anions, category 2 of inorganic anions. We arrived at the phosphate, hydrogen phosphate, dihydrogen phosphate. What happens is you can take two phosphates and you can condense them to make diphosphate and triphosphate and other types of oligomeric and polymeric centers. So I'm just gonna draw 3 lines to this phosphorus, but you take out water, so that's why they're called condensed, and you get a phosphorus oxygen phosphorus network. And so one of the examples I have is this mineral here. It's a fluoroapatite, so it's similar to our enamel. So our enamel in the teeth has some of these phosphate units replaced with carbonate units. And then you know about fluoridation, right? So if the enamel incorporates chlorine instead, so if you lack in your diet a source of fluoride, which is somewhat rare in the foods, carbonate, I can fix this carbonate thing here, right? And then your teeth become more brittle. So it's essential that you have in your diet that you have a source of fluoride, except of course our teeth are formed, so what's the point of the fluoride, right? So something to think about. But so that's just an interesting mineral here, good looking compound. I like those pictures. And speaking of which, here's another interesting phosphate mineral called turbernite, right? And so what happens is it's a granite, a type of granite. So however, the uranium here is not the issue, right? It's because it's 99% or 98% uranium-238, which is not the problem. It's the 235 that we're concerned about, and it's less than 1% abundant in nature. But it does actually trap radon gas, and we know radon gas is a problem. So if you have a granite top made out of turbernite, you may risk having radon coming off, right? And so so might want to check into that. Here's some arsenates and antimoniates. So antimony and arsenic are both toxics, usually the arsenic 5. That's the soluble, not 3, there's arsenic 3, arsenic 5. You can also have arsenic in lower oxidation states like -1. And so it's the soluble arsenic, not arsenic, it's the antimony. Both antimony and arsenic are toxic. But so thousands of years ago, this is a very soft stibnite. This is a very soft mineral, and you can grind it down into a paste, and people used it because it's got such dark black color, they used it in mascara and products like that. Of course, that's not recommended since it's not healthy. Also in utensils. So, but this is thousands of years ago by certain cultures. Here's another arsenic compound, and so here arsenic, if you think about it, if this is iron 3 and this is -2, so this has a -1 oxidation state, so it's easily oxidized to arsenic 5, which is soluble and toxic. So this is found in thermal vents and caves as such. And so here, really, this is pretty cool color. Arsenic sulfide here, orpiment. Again, this is found in thermal vents in Yellowstone Park, and ancient Chinese used this in medicine, and alchemists tried to use this compound to turn it into gold. I find the colors very fascinating. And so sulfur oxo anions, we know sulfite, sulfate, hydrogen sulfate, and hydrogen sulfite. Pretty easy. Again, it can also be a counter ion, as well as chelating and bridging in certain compounds. We can also have metabisulfite and thiosulfate. Thiosulfate, just you replace the sulfur, one of the oxygens, with the thio group. You've probably seen that. The metabisulfite you might not have seen, but it decomposes to give off sulfur dioxide and sulfite. So this is used in winemaking in larger potassium metabisulfite, or they call them Camden tablets. They can sell you, if you're a winemaker, you can buy those. It helps you disinfect your your glassware, and so of course you can add some to your wine. It'll preserve your wine a little longer. It's the sulfur dioxide that kills the bacteria, and it's the sulfite that we're concerned about, and some wines contain sulfite. So on a small scale you can easily sanitize just with heat, but on a large scale they like to add sulfites to their wines in Napa Valley and whatnot. So the halogenated oxo anions here, we have, you're familiar with all of those. Those are really strong oxidizing agents. If you think of chlorine, you think of chloride, oxidation state 1, but here we have +1, +3, +5, and +7, right? Of course, sodium hypochlorite is bleach, strong enough, but the perchlorate, perchlorate, right? So ite and ate, and then we have perchlorate and hypochlorite. For the naming, you can also replace X here with bromo. We can have hypobromite, we can have hypofluorite, so those are interchangeable. So again, these are all very strong oxidizing agents, and that's probably why bleach is used, because it's a good oxidizer, right? Okay, so group 3, most interesting to me, are the polymeric oxo anions. So silicate, there is actually no discrete silicate, SiO4. It is all tied up in silicates, which silicon actually makes up 95% of the Earth's crust, right? So we have most minerals silica based, and sand and glass is of course made out of these silicates. And so if you look at a discrete unit here and you put this into a tetrahedron, you get a shape like this. And so that's going to simplify the way we draw this. If I, for example, draw a dimeric silicate like this, you should understand that you should be able to deduct the formula here, right? So we have here, we're sharing, so we have Si2 centers. And then you can just count, if we're sharing, we've taken out 1 oxygen, so instead of 8 we have 0.07, and then also you are reducing the charge. Each of these oxygens here has a charge, and so if you're making an oxygen silicon bond, you are eliminating those 2 charges, so instead of -8 you're down to 6 minus. You can also just simply look at how many are not connected, so 1, 2, 3, 4, 5, 6, so this would have a 6 minus charge. So just understanding that these blocks represent a silicate unit, and that each connection means that an oxygen has been taken out and the 2 charges have been taken out. So here is that example drawn out. This is called sorosilicate, and then you make networks, chains, and bands, and ultimately you end up with quartz, which is a tetrameric network similar to the titanium alkoxides that I showed in lecture 1. So, and we can take this further. We can make ring structures like the cyclosilicate here. Again, you have 3 units here, so you have 3 silicons. I'm essentially deriving the formula and the charge here, and then you can either say, well, if we have 3 times 4, which is 12, but we have 1, 2, 3 connections, that means we took 3 out, so we're left with 9 oxygens. And then you also have to, for each connection you made, you have to take out 2 of the charges. So again, we would have a -12, but we take 6 out, so this is how we end up with the 6 minus charge here. Or again, you can just count 1, 2, 3, 4, 5, 6. Any corner that's not connected to another tetrahedron is going to have a residual charge, right? So then you can put ions in there to balance that out, and you can get different kinds of minerals, right? You can put magnesium and copper in there. I have a few examples in a minute. Germal is another ring silicate, all right? It's there's plenty of room here for cation to sit, all right? So we have again, we have these charges that are here, so this is going to have a 12 minus charge. Ingosilicates, sorry, it's called inosilicates, examples are pyroxenes, and so obviously, as I mentioned, we have charges. So we have this unit here that's repeating. Let's see if I can get it correct this time here. This is the unit in, and then I've conveniently left the charges out, but obviously we still have like 1, 2, 3, 4, -4 per unit, or 2 per unit, and I meant 4 per repeating unit. I'm not 100% sure, but obviously if we have anions, we need cations in the structure. I think I have examples here. Yeah, octite would be a chain silicate that has calcium, sodium, or magnesium, iron, or aluminum. So those are the different possibilities for octite type minerals. Here you see a beautiful greenish color, diposite, which is also chain silicate with magnesium and calcium inside of it. We have band silicates. That's a double chain, so we're reducing the charges even more. Chrysolite is one of the examples. So it's white asbestos. Of course, there's different kinds of asbestoses, and asbestos is naturally occurring, and when we bake it down, we get the blue asbestos, which is of course what we made, what causes cancer, because it gives off these fine particles and they get stuck in the lungs. Here's the naturally occurring, the white asbestos that you can see. Even that stuff's flaking off, so although they do say, if I read it correctly, this is not toxic, it doesn't become toxic until it's the blue asbestos. Here's another example. Oh yeah, that's the blue asbestos here. I forgot I had the example here. Yeah, don't take that home. Sheet silicates, phyllosilicates. Anyway, we are just expanding the network, and then to top things off, well, I'm not there yet. So again, blue color you're familiar with from copper, and bluish green. This is green here, magnesium. And so talcum powder is still commercially used. They grind down like 8 billion tons a year, and it's used in cosmetics and baby powder and this sort of thing as a desiccant. It's a big industry. Keep mining that stuff, right? We can have tectosilicates, which are then the quartz system. So we don't have any residual charges. We just have networks up. So you take those two sheets and you stack them kind of like you would diamond, and so this is similar. And it's quartz, and so here we have a quartz crystal. You can make any of those silicates by condensation. And so here just a couple of examples. So all you have to do is, if you're making 4 centers, you just need 4 of the discrete silicate anions, and then obviously you do your math. If you have 11, you went from 16 to 11, you should be able to predict the reaction for this. As long as you know what the product is, you should be able to come up with a reaction and the correct number of oxygens. This is just a basic balancing, and the charges, of course. So if I provide you with the formula for sheet silicate, you should be able to do the synthesis of sheet silicate from discrete silicate units, right? So it's always from orthosilicate, and then you just need a number of them to form your product. We have zeolites. Zeolites are highly important. They are used industrially as molecular sieves, or they're used in gel permeation chromatography or size exclusion chromatography. For the most part, they're aluminosilicates. Now, this particular structure I showed the picture of does not, but so we have these gaps here. Oh, black's going to be an issue, but you can see, you can put certain molecules in there, and you can cater the size if you're good with your synthesis, or you can actually create like 4 angstroms fits water, very nice, used in molecular sieves, if I remember correctly. And so here are just some of the examples of where zeolites are used. Desiccants, of course, selective absorbents, molecular sieves, filters, in gel permeation chromatography, which is different from what you've learned. I don't know, maybe you know about GPC, but it's not based on polarity, it's simply based on size. So if you wanted to analyze polymers, for example, and their molecular weight, what you do is, so it works kind of like the Pac-Man model, right? So you have these sieves with gaps, and instead of the substrate or the elutant that comes through your your column interacting with the surface, they actually, if they're small, they go in deep, they spend more time inside of this gap, whereas larger polymers go straight through. So when you see your chromatogram, if you have the very first band that comes off has larger molar masses than the other signals further down, okay? And also, the more narrow it is, the less distribution you have, right? Because you have a molecular weight distribution for your polymers. You know, they all have. Not every single chain has 10,000 carbons in a row. You know, some might have 10,450. So you see a wide distribution sometimes when you do gel permeation chromatography, or gel permeation chromatography, or size exclusion chromatography. So it's used quite a bit. So here are the formulas in general. Obviously, you still need, you're replacing those SiO2 units with AlO2 units, and so silicate, if this is +4, this is +3, you end up with a residual charge, and so you need to fill that in with metals. Here's a couple of examples of these. This is actually used as a food additive, so obviously it's going to add to keep your food dry, but you might find that on a well, maybe not anymore. They probably name it something like natural flavor nowadays instead of E556. So yeah, I probably named it natural flavors, my guess. Couple of examples. You can see the different size gaps. This one I think is 11 angstrom. Let me go and cheat and look this up. No, the larger gaps here are 4.2. Should have really written it down by 5.4 angstroms. And then the smaller gaps are like, well, no, I don't know. I'm not 100% sure. I have written down 3.5 by 4.8. So that probably just refers to these average larger gaps here. Here's another example. This is the one that has the largest gap that I could find, but it's not 11. It's 6.3 angstroms. That's the size gap. So anyway, just a couple of examples. Here's another one, and these are made by baking them, or okay. Group 14 oxo anions, germanates, and so we're going down silicon, germanium, tin, and lead. So now we're becoming more metalloid. No more. The metalloid character comes in, but they're analogous to the silicates. But then when you go over to tin and lead, obviously you have the higher metal character, and so you're not going to get these chains like you would for germanium and silicon. Of course, germanium is super rare. So here we go. Silicates make up like 95% of the Earth's crust. Germanates maybe 0.00095%, right? So germanium's pretty rare. One of the elements that was predicted by Mendeleev, but not found until after he predicted and people were looking for it, right? Borates, nice. Transitioning into boranes, which are boron hydrogen compounds. Some of my favorite things to put on an exam, and the very last thing I'll do to torture you, promise. So we have borax. Borax has interesting structural features. For starters, we can design, we have these tetrahedral centers and we have trigonal planar centers, and so that can lead to some interesting structures. So tetrahedral, and so the tetrahedral centers would have a negative charge. So we do need these counter ions. And then we have these trigonal planar boron flat centers. So borax, of course, is used in it can be used as a detergent. In the next section or the very last chapter, I will discuss boron and boranes and some of the borates in more detail, but for now, it can also be used as an antiseptic or cleaner, and has some useful features. But then we have, as I mentioned already, the condensed phosphates. I showed this reaction earlier here. Take water out, so you can get diphosphate and triphosphate. You can also get ring phosphates. We've seen them in minerals. And then finally, we have the transition metal polyoxo anions. They are either heteropoly, meaning there's only There's a couple of metals here as counter ions or isopoly, single metal, and I don't want to really go into any great detail. I want to go ahead and transition into the next chapter, which is more fun. The boranes have some cool structural features and reactivity, and then that's the last thing I'll do, and you can graduate with a degree in chemistry. But yeah, halide, last group, not much to say here. These all have to be, the metals all have to be Lewis acidic, sufficiently Lewis acidic enough to take upon an additional anion here, or a Lewis base, so it wouldn't work for something like magnesium, or would it? Because we got those Grignards, right? But anyway, this is it. This is the end. My quiz is going to be on naming, obviously. Okay, that's it.